Colligative properties are the properties that depends only on the number of the solid particles in the solutions and not on the nature of the properties of the solid particle. For examples, the vapor pressure lowering, boiling point elevations, freezing point depression, and osmotic pressure. Vapor pressure lowering. Okay, the presence of the non-volatile solids in the solution will decrease the vapor pressure of the solutions if compared to a pure solvent. Okay, then this relationship between the vapor pressure of the solutions and the vapor pressure of the solvents is depends on the concentration of the solute in the solutions. Okay, according to the Rath law, the vapor pressure of the solvent, which is PA, is equal to the vapor pressure of the pure solvents times to the mole fractions of the substance A. And this Rath law is only applicable for the ideal solution where delta S solution is equal to 0. Okay, when we have two different substance in the solution, for example, we have a benzene and toluene, which is both is volatile, means that they have a measurable vapor pressure, so that the vapor pressure of the solutions is equal to the sum of the individual partial pressure. So, the total pressure of the solutions is equal to the summations of the individual partial pressure and given by the Dalton law of the partial pressure. So the partial PA and PB is the partial pressure of the solution for the component A and B, while PA nodes and PB nodes is the vapor pressure of the pure substance, and XA and SB is their mole fractions. So that the total pressure PT is equal to PA plus PB, which is the partial pressure of component A plus partial pressure of component B. Why the vapor pressure of the solution is less than the vapor pressure of the pure solvent? Okay, vaporization will increase the disorder of the molecule, which is from the liquid to the vapor state. Okay, means that the greater the disorder will more favorable the vaporization process. Okay, the solution is more disordered than the pure solvents. That the difference in the disorder between the solutions and the vapor is less than the between the pure solvent and the vaporization, so that the solvent molecule have a less tendency to leave the solutions than to leave the pure solvent to become a vapor. So in short, means that the presence of the solutes will reduce the vapor pressure of the solutions if compared to the pure solvents, and this decrement is proportion to the concentration of the solute. So the presence of the non-volatile solute will decrease the vapor pressure of the solutions, thus increase the boiling point of the solutions. Okay, at any temperature, the vapor pressure of the solution is lower than the pure solvent. Okay, you can see here that the light blue is the vapor pressure of the solutions, while the dark color is the vapor pressure of the pure solvent, so that the boiling point of the pure solvent is lower than the boiling point of the solutions. Okay, the boiling point of the solution is higher than the boiling point of the pure water. Okay, let's say we have a salt solutions and the pure water, means that the boiling point of the salt solution higher than the boiling point of the pure water or pure solvent. Okay, the boiling point elevation or delta TB is described as the temperature difference between the boiling point of the solution TB minus to the boiling point of the pure solvent, which is TB notes. So that the boiling point elevation is proportional to the vapor pressure lowering and the concentration of the solutions, which is M is in molality of the solutions, and Kb is the molar boiling point elevation constant. The additions of the substrate or non-volatile solute will reduce the freezing point of the solutions. Okay, freezing point dispersion is defined as the difference between the freezing point of the pure solvent, which is TF naught, minus to the freezing point of the solutions. Okay, we can see from the figure here that the dashed line is the freezing point of the solutions, while the full line is the freezing point of the pure water. Means that the presence or the additions of the solute will reduce the freezing point of the solution, which is TF is directly proportional to the molality of the solutions, and KF is molar freezing point dispersion constant. Okay, freezing involves the transition from disorder state to the order state. Means that during this process, energy will remove from the system to get a to create a order state. Okay, due to the presence of the non-volatile component in the solutions, so means that it needs more energy to be removed from the system if compared to the pure solvents. So the freezing point of the solution will be lower than the freezing point of the pure solvent. For example, the presence of the salt in the solutions in the water will reduce the freezing point of the water, and methanol in water just boil at only 65 degrees Celsius if compared to the pure water. Osmosis is a spontaneous movement of the solvent molecule through a semi-permeable membrane into a region of a high solute concentration. Okay, for example, when we have two different concentration of the solutions, so the solvent molecule will tend to diffuse across the membranes from the less concentrate to a more concentrate solutions to a semi-permeable membranes. So you can see here that the we have a two compartment here that separate from with the semi-permeable membrane. Okay, which is on the left is the pure water, and on the right is the compartment that contain a concentrate solutions. So initially the water level at both compartment are equal, but after a certain period of time the level of the right tube begin to rise and continues going up until it reaches the equilibrium. Osmotic pressure of the solution is the pressure required to stop the osmosis, which can be measured directly from the difference in the final fluids level. Okay, it is defined as a external pressure required to be applied so that there is no net movement of the solvent across the membranes. Okay, osmotic pressure is the colligative properties, means that it depends on the molar concentration of the solute, but not on its density. Okay, refer to this figure, you can see that the vapor pressure of the water is higher than the vapor pressure of the solutions, and there is a net transfer of the water from the left beaker to the right one until there is no more water remain in the left beaker. Okay, the colligative properties of the electrolyte solutions is greater than the non-electrolyte solution because the electrolyte dissociate into the ion in a solutions. Okay, for example, we have a calcium chloride which is dissociate into the 3 ion, which is 1 ion of the calcium and 2 ion of the chloride. So, for the 0.1 molarity of calcium chloride, they should have a trace greater than 0.1 molality solution that containing the non-electrolyte, for example the sucrose. Means that 0.1 molality calcium chloride solutions is expected to have or to depress the freezing point 3 times much than the 0.1 molality of the sucrose solutions, because it has a 3 ion, which is the Van Hoff factor, which is I is equal to 3. Okay, Van Hoff factor I is equal to the actual number of particles in solution after dissociations over the number of formula units initially dissolved in solutions. So for the non-electrolyte, the I value is equal to 1, while for the strong electrolyte like natrium chloride and KNO3, the Van Hoff factor is equal to 2. And for the stronger electrolyte like natrium sulfide and calcium chloride, the Van Hoff factor is equal to 3. So the equation of the colligative properties is modified with the I value or Van Hoff factor. Colligative properties of the electrolyte solution is smaller than expected due to the higher concentration or electrostatic force from the formations of the ion pair. Okay, the ion pair is held together by the electrostatic force. Okay, so that the presence of the ion will reduce the number of the particle in the solutions and causing a reduction in the colligative properties. So electrolyte that containing the multi-charge, for example the magnesium and aluminium, will have a greater tendency to form a ion pair than the electrolyte that containing the single charge ion, for example NaCl and KNO3.